All right. Welcome everyone to today's seminar. Today I'm happy to be introducing Dr. Enrico Camporeale. Dr. Camporeale is a research associate at the University of Colorado Boulder and affiliated with the NOAA Space Weather Prediction Center. His research focuses on the use of machine learning techniques applied to space weather and space physics, and he is one of the co-editors of the recently published book, Machine Learning Techniques for Space Weather, and also serves as an associate editor for the Journal of Space Weather and Climate Science. Today, I'm happy to have Enrico here to discuss his recently published paper, Data-Driven Discovery of the Fokker-Planck Equation for the Earth's Radiation Belt's electrons using physics-informed neural networks. Enrico, if you would like to take it away.
Thank you. Thank you so much for having me. I'm going to start sharing my screen. And thank you for giving me this nice opportunity to share my work. You see the screen well, I guess? Can you hear me well?
Yeah, everything's coming through really good.
All right, very well. So yeah, okay, this is a list of the co-authors, collaborators. Need to acknowledge this NASA grant. So I've given this talk sort of a number of times for different audiences. They usually start with this one slide that explains the radiation belt, sort of in a nutshell. I believe probably this is now not really needed for this audience, but nevertheless, I'm going to go real quick through it. So everybody is familiar with what radiation belt is. I'm going to stop my video for just to have a better Wi-Fi. Looks like it's a bit slow on my side. All right. Hopefully it's still there. Is stopping? Okay. So anyway, you're all familiar with the fact that charged particles are sort of trapped or quasi-trapped in the Earth's magnetic field. And usually the way we like to think about the orbits of charged particle in the radiation belts are that they have three different orbits: gyro motion, bounce orbit, and Reith orbit. Each one of those is associated with the adiabatic invariant, first, second, and third adiabatic invariant. What I'm going to focus on today is the simplest case, that is when the third adiabatic invariant is broken. This is the easiest one to break because it's associated with the longest time scale. So if you assume that the first and second adiabatic invariant are still constant, then you can derive an equation, which is a radial diffusion equation, which I guess most of the people here are familiar with, which is this one on the top. I usually like to quote this famous statement or quote by the statistician George Box that all models are wrong and some are useful, because to me, this radial diffusion equation really is a sort of the quintessential wrong but useful model. And I will explain in a second what I mean by that. Now, again, just to be everybody on the same page, again, assuming that most of the people are actually familiar with this equation, F is the phase space density. So this equation actually describes the change of phase space density in time, which undergoes a diffusion in L, which is again the third adiabatic invariance, or L star, the equatorial radial distance, units of Earth's radii. T is the time, which is usually in units of days. DLL is the diffusion coefficient, and tau is the electron lifetime. So, and again, this radial diffusion equation is intended for fixed values of the first and second adiabatic invariants. The diffusion, of course, happens in this first term, and pretty much everything. I mean, the idea is that everything which is not captured by radial diffusion sort of falls as a loss source or loss term in this second term, F over tau. Now, quasi-linear radial diffusion has been the focus of intensive investigation in magnetospheric physics for more than 60 years now. I've just put down some of the early sort of landmark papers, as you can see, started from the 60 or 66, 70. A lot of work and studies have been done in this field. and still nowadays, I think it's a topic which is very much studied. You can find papers published even this year about quasi-linear radial diffusion in the radiation belt. So why is this model useful? Well, for a number of reasons. First, because it sort of follows the argument of parsimony, follows the famous Occam's razor argument. And again, quoting George Bock's paper, says, since all models are wrong, the scientists cannot obtain a correct one by excessive elaboration. So on the contrary, following William of Occam, he should seek an economical description of natural phenomena. And then Bock also says that the ability to devise simple but evocative models is the signature of the great scientist. I like this quote very much. So of course, this is a parsimony a model that follows this parsimony argument, because it's computationally expensive. It's 1D plus time, so it's possibly the simplest model you can think of. Yet it is non-trivial, because a very rich family of solutions can actually be recovered when tau, this term here, the electron lifetime, is general enough. And finally, of course, it is physics-based. It's not just an assumption that one makes from a mathematical standpoint. It is rigorously derived starting from Blasov equation. So it's physics-based, and in fact, it contains most of the physics responsible for the particle dynamics, and indeed, it has been proved successful in many cases. In fact, until maybe 10 or 15 years ago, this was the main model that was studied for transport of electrons in the radiation belt. On the other hand, why is it quote unquote wrong? Well, because again, it is derived within kinetic quasi-linear theory. So there are a number of assumptions that this equation is based on. So of course, whenever one of these assumptions is not satisfied, this equation is not really valid. I'm not gonna really go through all the number of assumptions that, you have to assume some sort of wave spectrum. Of course, there are no nonlinear interactions, because it's so you can only capture low amplitude fluctuation. There is something called the resonance limit. And then at the end of the day, all the wave particle interactions are sort of lumped into this number here, the diffusion coefficients. So in fact, there have been a number of studies that shows non-resonant heating. These are just a couple of papers that I worked some time ago. There are, of course, many others. So, of course, just to say that this is, there are a number of assumptions that have to be fulfilled for this equation to be valid. And even when quasi-linear theory works fine, there are still multiple sources of uncertainties in estimating or calculating the radial diffusion coefficients. So first of all, you have to rely on a given model for the background magnetic field. Usually we always bounce and drift average, so there's no MLT dependence. There are a number of approximations here. You don't take into account the azimuthal wave structure. And in fact, if you look at the literature for like the last 20 or so years, there have been a number of different parameterization of the diffusion coefficient, and each one, if you plot them, each one gives you sort of a slightly different result. So this list is sort of adapted from this nice paper that I recommend, Bentley et al. 2019, capturing uncertainty in magnetospheric ultra-low frequency wave model. So what I'm gonna present on and focus on today is an inverse problem statement. So again, starting from the idea or the assumption, if you like, that this equation is good enough in a sense to describe transport of electrons in the radiation belt, the inverse problem statement is the following. What is the optimal choice? So here we have two parameters, physical parameters, but you can think of this as free parameters in the equation, DLL and tau. So what is the optimal choice of those parameters that makes the result of the diffusion equation most consistent with data, assuming that you have, you know F, you can take F from data. I'm going to use Van Allen probes data. So this is known as an inverse problem. meaning that we know the result, we know F, the phase space density, and we want to infer the inputs, in this case, the free parameters DLL and tau. And this is usually much harder than solving the forward model, meaning using a given model for DLL and tau and solving this forward in time to obtain F. Why is it much harder? Because usually, typically, inverse problems are ill-posed. For instance, they don't have a unique solution. Now, the standard way of approaching inverse problems in physics or in geophysics, standard statistical approach is a Bayesian parameter estimation. So this is not really the focus of this talk here, but I thought I was going to just mention this for a few minutes. There is a paper published 2 or 3 years back that does exactly this, the Bayesian inference of quasi-linear radial diffusion parameters using Van Allen probes data. So again, it's a classical topic in geoscience, but I believe it's still not yet a mainstream approach in space physics. I think it should be used more often. One of the weaknesses of this approach, and the very reason why I moved forward then using PINNs, and I'm going to explain in a second what those are, is that this approach is very difficult to apply in higher dimensions. So it works well in this case, which is just 1D, well, it's 2D really, it's 1D in space plus time, but it's much harder to apply in 2D or 3D. And the reason is that basically this requires a Markov chain Monte Carlo approach, which means that you have to solve the equation many, many times, like 50,000 times, that sort of order of magnitude. And again, if it's a 1D, it's computationally inexpensive, you can do it, but solving a 2D or 3D equation 50,000 times might become unfeasible. So again, just gonna go real quick through the results of this MCMC approach, Markov chain Monte Carlo approach. This still requires, and that's yet another weakness that I wanted to overcome by using PINNs, this still requires the parametrization of diffusion coefficient and electron lifetime. So once again, if you look at the literature, there are a number of parameterization. I think the most popular for DLL is this one by Brautigam and Albert here on the bottom, proposed, 20 years ago. And then there are a number of parameterization for tau, like this one from Orlova. Of course, you can maybe even over-parameterize a coefficient. We try to keep things simple. So we actually use exactly the same parameterization as Brautigam and Albert for DLL. So now you can see it's exactly the same formula where A, B, and C now are the free parameters. And tau is also quite simple polynomial expression, which is actually L square for L smaller than LPP, the plasma pose location, and it's just a constant divided by Kp for L larger than LPP. Then once you run this exercise of running the Monte Carlo experiment, you end up with a posterior distribution. So the idea here is that each one of these A, B, and C parameters are sort of random variables, and they come with their own, what it's called in Bayesian statistics, posterior distribution. So you can see sort of the spread. So you do not just get a single number, but a proper PDF for each one of these numbers. And then you can compare, this is what was done in that paper, for different values of Kp, compare, for instance, the DLL obtained by this method, or at least this is the mean, again, because we have a distribution. Compare with Brautigam and Albert, you can see there are small but not insignificant differences. Okay, as I mentioned, that was not really the focus of the talk. I just mentioned it for sort of completeness. The focus of this talk is this different approach to parameter estimation, which is based on a machine learning technique called physics-informed neural network. So here I'm gonna, I put on this slide the two references. So the references on the top is the main reference for PINN, and you can already see from, so this was published in 2019, only 3 years back now. already got more than 3,000 citations. So this is already a sort of sign. It can tell you that this is a really powerful approach that is becoming more and more popular, at least in the applied math and machine learning community. I believe this is the first time it has been used in space physics context, and this is on the bottom is the paper that contains all the results I'm going to show in the next half an hour or so, and has been published in JGR earlier this year. And the co-authors are George Wilkie, Sasha Drozdov, and Jacob Bornik. So let me spend a minute first to describe what are physics-informed neural network. Unfortunately, this might require a little bit of prior knowledge about neural networks in general, but hopefully I will be able to explain it well. And if you have some question, I can, of course, try to answer them at the end. So in a standard neural net, so the neural network, first of all, is just a way of solving an optimization problem where you define a cost function that you want to minimize. And typically the cost function is this guy here at the right-hand side, the second term, where f is the output of your neural network, and you have some observation of some data for that given output. You just want to minimize some sort of an error or a residual or a norm with respect to between f, the output of the neural network, and the observation. Now, the very simple idea, if you like, of PINN is to say, okay, on top of this residual here, I would like to minimize a partial differential equation or a residual of a partial differential equation. So you can see that when the equation, this is the equation we're focusing on, when this is exactly solved, this term here becomes zero, basically. So you add this term in the cost function, and the way, sort of the trick under the hood that allows you, or allows the neural network to solve this, is what is called autodiff, or automatic differentiation. And it's really simple in a sense. It relies on the fact that no matter how hard or deep or complex your neural network is, it will always give you as an output a function which is analytical and differentiable. Exactly. So what it means is that all these derivatives, the f over dl, the f over dt, all the derivatives really, can be computed exactly by this idea of automatic differentiation, simply using the chain rule. So there's no numerical or discrete derivatives here. There are exact derivatives computed exactly. So what this means is that PINN is both basically a gridless method to solve a PDE on a set of points, so to solve the forward problem, and a way of estimating the coefficients of a PDE. And this is what I'm going to focus in this talk to solve the inverse problem. So how does it work? How do you use PINNs for parameter estimation? This is, again, a very general setting. Assume you have a PDE, which is just df over dt plus a nonlinear term h, which is a function of f, plus some free parameters d and c. What you do in this case, for instance, and this is, I mean, example that applies to our case here. Let's assume we have only 2 free parameters. What you do is the following. You train 3 different neural networks, independent from each other. The first one outputs f, the second outputs d, and the third outputs c. They all take as an input only space and time. So x here for us would be L, and time t. So they see sort of each point in your domain, and they output these 3 parameters. And then the 3 parameters are sort of, they go together in the loss function, which is again the typical mean square error plus the residual of the PDE. Now, when you train this architecture, you do the backpropagation. Basically, these 3 neural networks are trained such that they output the optimal value of f, d, and c as a function of space and time. Now, there are, well, I put the title of this slide a question not to ask, simply because I've realized every time or oftentimes, I present the PINN, there's always some sort of misunderstanding. So I just wanted to put this up front to clear up any misunderstanding. Because one of the questions that might come up is, how can you predict the phase space density simply as a function of space and time? Because as I said here, the only two numbers that enters into the neural network as inputs are space and time. And again, this is just a misunderstanding because I'm not really predicting anything, or at least not yet at this stage. So the idea to understand PINN is the following, is that the neural networks are a universal function approximator, which means that with enough complexity, or enough number of weights, any function can really be fitted exactly on a finite number of points. So if you throw some data to the neural network and the network is complex enough, you can find a fitting function that goes through this data. Now, all the PINN does really is, of course, there are infinite number of functions that go through a finite number of data points. All the PINN does is, among these infinite number of functions, to choose the one that also solves the PDE on those set of points. So you can think of that extra term, the residual of the PDE, as a sort of regularization term for the neural network that sort of forces the neural network to converge on a fitting function, which is also a solution of your PDE. So again, it's a very simple idea, but extremely powerful. Now we have to do a little step back here into applying this technique to the Fokker-Planck equation for a simple reason. So I was talking about this top equation here, the standard equation for radial diffusion, that again, everybody or most of the audience, I believe, is familiar with. Now, this is simply too ill-posed to be solved as an inverse problem. The reason is that if we allow, again, DLL and tau to be too general, so without prescribing a given parameterization for DLL and tau, which is exactly what I want to do using PINNs, this becomes too ill-posed because you can simply, you can easily see that, if somebody gives you a functional form for DLL, or not even a functional form, actually, somebody gives you DLL point by point in space and time, you can invert exactly this equation for tau. So in other words, for any given value of DLL, there is a value of tau such that this equation is solved exactly. So this doesn't help us very much because essentially there are infinite combinations of DLL and tau that solve this equation. So what we have done here is to sort of step back from this radial diffusion to a more general form of a Fokker-Planck equation, which is a drift diffusion equation. So the diffusion term is still the same, but we replace this f over tau term with a advection term where we use a drift coefficient. And so this is going to be the focus of this inverse problem that I'm going to study now. Now, before going on, there are a number of baseline models that we use to compare the results. Again, there are large numbers actually in the literature. What we've been using in the paper are these three models. So for DLL, we use the Brautigan and Albert, published in 2000. The second one here is Ozeki et al. And the third one is a paper by Ali et al. While for tau, I believe that possibly the only, or anyway, the most popular parameterization is this one where you split, you divide your space in L smaller and larger than the plasma pose location, and you have two different simple parameterization where for L larger than LPP, this depends on KP. So you can see that what all these parameterizations have in common is that they all depend on L and KP, the geometric index. Of course, there are some details here, how we estimate the plasma pose location. It's typically done by using an empirical formula from this paper, Carpenter and Anderson. And then when we use this sort of parameterization in the forward model, we used a scheme which is stable, unconditionally stable, has been explained in this paper back in 2012. Then we also had to define some errors, some metrics, if you like. These have been taken from this paper, Morley et al., published in Space Weather 2018. There are basically two basic metrics. This one on the left is a measure of accuracy, and this one on the right is a measure of bias. And the one in the bottom is a relative error of the log of phase space density, which is maybe sort of easier than the other two, and what most people actually use is just a relative error, basically. This P50 means the median value. So we define an error as a function of L only, and then we take the median value, basically. All right, so looking at the data and the results now, so we've used about 4 years of an Allen probes data, sort of arbitrarily, if you like, splitted. So the first 3 years has been used for training and validation and model selection, essentially. And then at the end of the talk, I'm going to show results on this 1 year of test data. So the basic point is that this is unseen data. So this 1 year of the test set has not been used for training or validating the model. So all in all, we have about 500,000 data points, and those are the values of the first and second adiabatic invariants for this study. Now, crucial point is that when you use neural networks, they are sort of stochastic objects, meaning that every time you train a neural network, you might, and in fact you will end up with a slightly different solution just because you start with a slightly different initialization. So what we've done here to sort of overcome this problem, because at the end of the day, we only want one solution for DLL and tau, is to train an ensemble of 20 different PINNs, physics-informed neural networks, look at the relative errors in the training set with respect to the ground truth, to the data, and then pick the 5 solutions which are the best in terms of relative error. And this is what is shown here, where the top row are the diffusion coefficient DLL, and the bottom row are the corresponding drift coefficient C. You can see that the general trend is very similar, although specific features are different and may appear in one realization and not in the other. Now, the crucial point here is that the PINN allows you, by means of this mechanism that I just described, to give you the optimal, so as an output, you get the optimal value of the coefficients in space and time. So here's space, of course, L is on the vertical axis and time is on the horizontal axis. And I believe that this is possibly the only method to solve an inverse problem that gives you this very general output of determination of the coefficients in space and time without prescribing a parameterization of those coefficients. So what we've done then, again, because we only want to work with a single value of DLL and C, is to simply take these 5 realization and take the average of that. So as simple as that. And are the results on the training set. This is maybe not surprising. So again, this is epsilon is the relative error as a function of L, average over or the median over the time considered in the training set. Now you can see the first 3 lines, blue, sort of orange, and yellow are the 3 parameterization baseline that we used. This black line, those are 5 lines, which are the best 5. And then the red line finally is the mean value. So it's the output when you take the mean of the diffusion coefficient and the drift coefficient, which are plotted here on the top. Now, already the fact that the red, taking the means of the coefficient gives you a performance or an accuracy which is comparable to each one of these best 5. This is non-trivial by itself, but we haven't really looked at the reasons why this is. Also, as I said, it's not surprising since this is the error on the training set. It's sort of designed to be low in a sense, so it outperforms all the baselines. But this is now the crucial point: is that once you have determined the optimal coefficients, the diffusion, the drift coefficient in space and time, this is really our gold mine, or our diamond mine here. Because all the physics of interest is sort of embedded in this coefficient. So you can think of all sorts of statistical analysis here to try to understand what is going on. Because again, these are the optimal coefficients that once you, with the assumption that this equation works well enough, once you fit these coefficients into the equation, you get the best output in terms of matching the data. And that's exactly what we've done. We've done a good amount of statistical analysis of this coefficient. What is shown here is the distribution of, well, in log space now, because it's simpler, of DLL as a function of L. The gray area here is the 25th, 75th percentile, and the orange line is the median value of DLL. So you can see that there are sort of three different, 2 or 3 at least, different regimes where the slope of DLL changes with L. What is plotted here are L to the 10 and L to the 20, simply because L to the 10 is the parameterization used by Brattigan and Albert. You can see that it might be good enough up to L equal 3 or 3.5, but then for larger L, maybe L to the 20 is a better parameterization. What is shown here on the right is a rank distribution. So this is takes a little bit of time to digest. What is shown here is for any given value of L. So if you take a sort of vertical cut here, the colors give you the rank, meaning that for rank 1, this is bin, obviously, in the log 10 of DLL. So that particular bin is the value that takes the most of the times DLL takes that value. And you can sort of see, different trajectories here. And it's even more clear if you look at CLL, at C, the drift coefficient. You really have different realization of C, where there's sort of a blank space. So in other words, it's, C is most probable here, even on this plateau here, or going up. And you can see, again, different physical realization of C. The spread is larger for C here, but again, you can see at least 2 different regimes for L smaller than 3 or 3.5, L larger than 3.5. Okay, the next step after you do a statistical analysis is a feature selection. So in sort of machine learning jargon, feature selection means sort of studying and understanding what are the inputs. So if you want to, again, parameterize DLL and C in terms of some given inputs, which one are the one that carries the more information. And we used a simple method called backward elimination, which is based on a generalized linear model. So in other words, we have trained a model that outputs DLL and C so we have selected a number of inputs like L, the phase space density, the average of phase space density, the boundary condition, and then all linear combination of these parameters, KP, and so on, up to second order. And when you use all parameters, of course, you get the best possible model, and this is the value of R squared, the coefficient of determination for all parameters. And what this plot shows is the value that you get if you only use L. You already get 0.95 almost. So this tells you that L is the most informative input for DLL. And then, again, the way to read this plot is when you add a second feature on top of L, so you have 2 inputs, 3 inputs, 4 inputs, and so on, you see that the accuracy of the model increases and increases, but at some point it saturates. So possibly 5 or 6 inputs here are good enough to describe DLL or C. Now, one important point is that Kp, which you might remember is one of the key parameters in all the parameterizations in the literature. Well, it comes at the 5th or 6th place as an input for DLL, and not even in the top 10 for C. So the next question we ask ourselves is, can we actually parameterize DLL and C without using the Kp? Or in other words, can we then forecast unseen data? So in order to forecast unseen data, you have to have a mechanism that produces or predicts DLL and C as a function of some of these inputs, again, for unseen data. So at the end, after we've done this feature selection, we had decided to use these 5 or 6 inputs, L, the value of F, or phase space density, at that given point in space and time, a running average of the phase space density over L, and then the boundary condition. So I forgot to mention here, for this study, we used boundary conditions at L equal 2 and L equal 5.5, which are taken from the data. And then again, a crucial point is that we don't use Kp. So this is different from all other parameterizations that have been used in the literature. Now, sort of a technical nuisance, by using the phase space density as an input for DLL and C, for the coefficients, this makes the problem nonlinear. It's not any longer quasi-linear, because again, the coefficients now are function of the output F. So numerically, this means that you have to do something like a predictor corrector method. But again, it's just a technicality, if you like. So in conclusion, this is the parameter estimation pipeline and the way we then use this to forecast new unseen data. So of course, we start with a strong assumption, if you like, that the physics obeys this form of the Fokker-Planck equation, which is a drift diffusion equation. Then by running PINN, we obtain the optimal coefficients, DLL and C, as a function of space and time in our training set, which was 3 years of data. Then by using this information, we run a feature selection. So we ask ourselves, how can we parameterize these coefficients in terms of inputs we have access to, like L, the phase space density, the boundary conditions, and so on. Then, and I'm not going to really get too deep into this, but we train a different machine learning model, a boosted regression tree in particular, that is used to predict DLL and C at any given time. So this will be used to give you the new value of DLL and C while you solve this equation forward in time. And then again, with these new values of DLL and C, you can plug those in and solve the equation with what I call the PINN discover and machine learn coefficients. And then you can get actual predictions for unseen data. And now this is the result on the test set. Again, none of this data. This is 1 year of data which has not been used in any of the previous pipeline. Okay, there are 2 plots here. On the left is the same format as previously. So L on the vertical axis, epsilon, which is the relative error on the horizontal. So the results for PINN are is this black line, and the 3 baseline, Bratin and Albert, Oziki and Ali, are the 3 colored curves. And the bottom line here is that oftentimes the results from PINN is more accurate. Around 3 is maybe a little bit worse, or anyway comparable. And then from 2.5 to 2 is again much better. I have to again remind you that all of these, when we solve the forward model, we use the boundary condition from the data. So by construction, the error goes to 0 at L equal 5.5 and L equal 2. And on the right here is a heat map of this same information. So epsilon here, this is averaged over time, and here is that same metric but pointwise in time. You can see that. So this result here is on the top left, and the other three baseline are the other panels, and you can see that this outperforms very much all the other baselines. These are two cuts for L equal 5 and L equal 4. I'm not going to spend much time on here, but just to show that. So the blue line is the data, the Van Allen probes data. The purple line is the PINN, and you can see that oftentimes they are one on top of each other, while all the other baseline tends to underestimate the phase space density. Now, the sort of next step forward is what I call the, if you like, the final frontier, which is the interpretable AI. So in the pipeline that I just showed you, there was some, the model itself was sort of opaque in the sense that there was this step when you train a machine learning model to predict new values of DLL and C, and that's not exactly clear, even though it was an ensemble of regression trees, so it was a little bit interpretable, but it's still a black box machine learning model. So the next step, what we've done is to get rid of this step and instead think of how we can parameterize. So these are the plots that I already showed earlier on. It's just the distribution of DLL and C, and here overlaid on these plots are this black line, which are cubic interpolation. So the question is, can we simply find a fit or interpolation of these two coefficients as a function of L only? The reason to choose L only because, as I said, L is the one parameter which is the most informative among them all. So if you do this exercise, you come up with these two formulas where again in log space, DLL and C are parameterized as cubic function of L. Now it becomes interpretable because basically you get rid of this machine learning model in between here, and you can directly feed this function of DLL and C into your equation. And when you do this equation becomes parameters free. So it only depends on boundary conditions now. And those are the results in terms of these two metrics I introduced earlier on, the symmetric percentage accuracy and the symmetric sign percentage bias. So the bottom line here is that the equation solved with the PINN-derived cubic fit is this black line, which again is there are error bars here, but it's very comparable with the other two baseline model, Rattigan-Arbor-Ozicki. Here I didn't plot the Ali result because it was just much larger in this scale. So it's either comparable or at times even better than the two parameterizations. And once again, this is a parameterization that takes DLL and C as function of L only. So again, when you plug these functions of L only in this equation, you have no free parameters anymore. It's just an equation that depends on boundary conditions. And the same argument goes for the bias. Now, in the last few minutes, I'm going to discuss another couple of results. Once you have done all this machinery, there's really a lot you can dig into and you can understand on these coefficients. So the one question one might want to ask is, what is the relative importance of diffusion versus drift? Because now we have these two terms. So we have defined this ratio here, R, which is exactly that is the ratio between the drift term over the diffusion term. And this is plotted now in log scale. So this black line on 0 means that the two terms are pretty much equivalent. And you can see that up to L equal 3.5 or 4, the drift is as important as the diffusion, while for in the outer part of the radiation belt for L larger than 4, it is basically the diffusion dominating over the drift. So this becomes more than 0, meaning that the diffusion is the one that dominates. yet another thing you can play with this machinery is automatic event identification. Now, an important point is that once you have defined your cost function, you have access to the information of the residual of the PDE pointwise in space and time. In other words, you can sort of see how well that drift diffusion equation is solved, or how well it matches with the data. And by doing that, you can do, again, automatic event identification. So what is shown in this plot here, these sort of vertical red lines are time periods for which the equation is not solved very well. So what that means is that the assumption behind that equation are not well satisfied, which typically means there are some nonlinear effects at play. And again, this is done completely in an automatic fashion. Then what we have done later on, after we have identified these about 12 or 15 events, which are summarized in this table, we looked at the literature. We found out that most of these events, these time periods, were actually already identified in the literature, and they're associated with dropout events or CME associated storms and so on. So majority of them are actually have a number of papers that study those events. Some of them are actually, I didn't find anything, meaning that either they have not been studied, or it might be a possibility for somebody working with data to look more carefully at those events. And again, this heat map here shows sort of these yellow islands are place and times where, okay, this is sort of a saturated heat map color, but it's place and time where the PDE is not solved accurately enough with respect to other place and times. Okay, I'm coming to my conclusions here. So I really believe that this methodology, physics-informed neural network, or this technique, if you like, is a game changer in applied math. Possibly the best way we can use it in our community or in space physics problem is to solve inverse problems. So I just show a sort of use case where you can derive diffusion and drift coefficients for radial transport for electrons in the radiation belt. And once again, you can do a number of things with PINN. We'll just sort of scratch the surface here. First of all, you can assess when and where in hell quasi-linear assumptions are not valid. By doing this, you can automatically identify interesting events. Something I didn't really touch upon is that you can redefine electron lifetime. So if you still really want to write your equation in terms of a F over tau term, you can derive an optimal tau in this way. You can definitely improve the accuracy in either nowcasting or forecasting. Crucial point is that you don't have to use future KP values, which to me is sort of the weak chain in using this equation to do prediction, is that sort of shifts the problem into predicting KP, which is just as hard as solving the Fokker-Planck equation and so on. And then finally, I showed that you can reparameterize the diffusion and drift coefficients with simple interpretable relationships. So this is the reference down here. I just wanted to conclude, take an extra minute, sort of give some announcements. So I believe most of you will join the AGU fall meeting, either in person or online. We have in the nonlinear geophysics section, we have a session on machine learning in space weather. We have actually 4 oral sessions about 80 abstracts and so on. So we have talks all day on Thursday, and we have a poster session on Friday morning on the AGU. So I hope to see many of you there. And finally, there is still a call for paper for sort of the special section in AGU journals, which is called Machine Learning in Heliophysics. Deadline is 31st December, but possibly could be extended to early next year. So in other words, if you submit a manuscript either to space weather, JGR, GRL, or ESS, you can select, when you submit the paper, you can select to be part of this machine learning in heliophysics collection. And this is all I have. Thank you.
Thank you, Enrico, for a really cool talk. We do have a couple questions regarding some of the machine learning stuff, so I'll read them out. Eric Winter has a question going back to the ensembles that you showed closer to the beginning of the talk. How is the ensemble generated? Is it just a different set of initial values for the network weights?
Correct, yes. So there is a technique, I don't remember the name now. It's a very popular technique to generate the weights for the neural networks, and which the weights are sampled randomly. So we just use that 20 times. So it's just different realizations of initial weights for the neural network.
Oh, okay. And George Cuck has a question regarding the kind of overall analysis. How do you think the coefficients might change during the solar cycle? Do you think you might see different DLLs if you looked at different solar cycles?
Yeah, that's a good question, actually. So I don't know, possibly. Of course, in order to answer that question, one should rerun the analysis using data on we only use 4 years of data. So, everything we can say, it's bounded to these 4 years. But possibly if you redo the analysis using data from a different solar cycle, which you might not have, you will get different results, possibly, yes.
Yeah, that's probably the biggest problem. The only other data you could grab PSD from would be CRESS, and that was only a few months. So
right.
So we have a question from Pranali Thakur. How deep can radial diffusion get during intense geomagnetic storms? Are you able to investigate that with your model?
How deep in terms of how much into L values?
Yeah, like how close into the Earth?
Yeah, again, I don't know the answer to that, but it's something that definitely one should be able to investigate. But again, this the one thing about this particular approach is, in a sense, because we don't use KP, sort of the values we find for diffusion and drift coefficients are sort of averaged over a long period of time that takes sort of merges the storm time and non-storm time. But one should, definitely should be able to just focus on storm times and see how much radial diffusion happens during those times.
And so I just have a final question for clarification. In your final model, the DLLs, the DLL and C, they're only dependent on the outer boundary conditions, so PSD at the largest L?
Outer and inner boundaries. So we talk both boundaries.
Both boundary conditions. Okay, cool. Jerry Manweiler has a question. Jerry, if you want to just unmute and ask.
Yeah, this is based upon what you just asked. We have longer running data sets, for instance, GOES. So if we took a GOES data set and ran that over time through your neural net as the outer boundary, and we did some proxy, such as ground-based magnetometer, something like that, for an inner boundary, do you think this would be successful in still calculating the coefficients as well as they have with the Van Allen data?
Okay, let me see if I understand the question correctly. So yeah, you can take different ways like GOES or ground-based magnetometers to infer the boundary conditions. And so you're referring to the final model. Once you have this parameterization for the coefficients, all you need really are the boundary conditions. So if you believe that those boundary conditions are, in a sense, consistent with what you will get from Van Allen probes, then sure, you can use that and run your model forward in time. Was that your question?
Yeah, I mean, that's more or less the question, is to understand whether we can use other boundary conditions that are not inherently Van Allen. and still work with this data, these coefficients that are derived out of the Van Allen, and this is assuming that consistency, as you point out, that the data is consistent with the other boundary conditions.
Yeah, I guess, yeah, it really shifts the question to, to how consistent those boundary conditions are, because if there's any error or any discrepancy, between the two sources of data, these errors will sort of creep into the model, right? So you will get a solution for your F, which has some inherent error. But
that error also would be reflective of the differences between the measurements of GOES and the measurements of Van Allen out at L equals 6.5 or 7.
Yeah, exactly. So I think the best way to do it, if you want to do it the way, would be first to do an analysis of whether there is a consistent bias or some shift between the two measurements, and then maybe adjust. Because again, the boundary condition you need to input into the model is something that what Van Allen probes would see, right?
Right.
But since, if you don't have that, you have to sort of have a proxy from GOES, but maybe with some sort of adjustment. So if you can figure out what is that bias, which I'm pretty sure there is some sort of discrepancy, then sure, this is, I think it's a robust way of doing it.
Okay, thank you.
Sure.
All right. Well, thank you again, Enrico, for a really interesting talk. Our next seminars will be a set of early career seminars next Monday. Francis Staples will be talking about radiation belt dynamics from a particle perspective. And Kazai Al-Shaid will be talking about comparison of solar wind modeling framework of ground-based magnetic perturbations with ground-based magnetometer stations during 54 geomagnetic storms. So again, thank you, Enrico, and I hope everyone has a wonderful week.
Thank you for having me. Bye, everybody.